Thank you all very much for coming this evening. So the agenda for tonight, we're starting off with Dr. Michelle Collins here, who's a reader at the at the University of Surrey in the Astrophysics department, who's going to talk to us about low surface brightness galaxies. And I have to say, I'm personally looking forward to it. I told Michelle earlier on, when I was a graduate student, I remember going to a conference of theorists, and an observer stood up and put an acetate on the projector and said, there are 4 low brightness galaxies on this acetate, and none of the theorists in the room could see them. And we said, and Michelle tells me that that's going to come up, that theme. So with that, well, I look forward to hear what Michelle's got to say. After the break, we've got who's very kindly going to talk to us about a visit she made to the European Astronaut Centre, and then she's also going to do what's up. If anybody's got any questions or thoughts after that, very welcome to hear them. And one final thing, the month, if any of you are becoming committee members, just drop me a line or drop another committee a line and just let us know. And if it's in a particular position or anything you want to do to help out, it would be great. And with that, I'll pass it to Michelle. So thank you very much. Right.
I'm sure you're live. It's entirely the wrong thing. Great start. There we go. All right. Okay. See if I can get this attached. I should do. Hopefully everyone can hear me. And I want to say thanks very much for having me this evening. I've been looking forward to giving this talk all week. And what I want to talk to you all about today is the work I do here at the University of Surrey. So I'm mostly an observer, and I observe things that look fairly uninspiring at first glance, but turn out to be very informative about what the universe is made up of and how galaxies and stars are forming and evolving over cosmic time. So what I want to talk to you about is hunting for the faintest galaxies in the universe. And in the background of my slide here, I have what I would define as an extremely bright galaxy. So this is the Fornax Dwarf Galaxy. It's a small dwarf galaxy that's orbiting around the Milky Way. And its brightness is about 10 million times that of our sun. So much, much fainter than the Milky Way, obviously. But in the dwarf galaxy regime around the Milky Way, this was something that we would call one of the big, bright classical satellites of the Milky Way. So this is kind of the upper end of things I look at. Fornax is a very interesting dwarf galaxy for many reasons. It's been well studied over the years to give us insights into what kind of the structure of these dwarf galaxies look like, and in particular, the kind of dark matter halos that are hosting them. But it turns out the even fainter ones can tell us maybe even more about that. And that's kind of what I'll get onto later in this talk. So in terms of the faintest galaxies of the universe, I'm kind of going to cover today, what do they look like? And why we should be interested in studying them in general. And yeah, we're going to go through that and discuss that in more detail. But before we do that, I have to ask what sounds like a very naive and embarrassing question for an astronomer to be asking everybody in the room. And that is, what is a galaxy? And it sounds very straightforward. We all think of a galaxy. So sort of, you know it when you see it. What a ridiculous question, Michelle. Why are you here? But it's actually become quite a contentious question at the kind of conferences that I attend. Just a few years ago at the European Astronomical Society meeting in Valencia, I got into a very lengthy debate over what you can and cannot call a galaxy that spilled out onto Twitter and became the talking point for about a week in the astronomy community. And I'm not entirely sure we ended up all agreeing, but what is certainly true is that I was probably right. Unlike NASA, this is the galaxy definition on the NASA website. So what NASA would define as a galaxy is a huge collection of gas, dust, and billions of stars in their solar systems. And a galaxy is held together by gravity. And our galaxy, the Milky Way, also has a supermassive black hole in the middle. Now, I'm very pleased with that last sentence, actually, because I used to use this in my cosmology course. And it used to say all galaxies had supermassive black holes. And I had a big red pen through that, because not all galaxies have supermassive black holes. But they've updated that, so at least that's correct. However, the rest of it still needs some red pen. So first of all, huge. That's very subjective. What does it mean to be huge in galactic scales? It could, huge, the Milky Way is massive, but the dwarf galaxy I just showed you is much smaller. Is it still huge? Is the solar system huge? What does huge mean? So I think that's very not quantitative, so we don't like that. And then in terms of gas, dust, and billions of stars, these will all be wrong as well. So we'll start with gas. Not all galaxies have gas right now. They must have all had gas at some point, because that's how you get stars in a galaxy. You cool gas, and then condense it, and you form a bunch of stars out of it. But many of them lose the gas in the course of their lifetimes, either because they blow it out themselves or it gets peeled off because they're orbiting a more massive galaxy. So most of the galaxies I study have no detectable gas in them. Same is true for dust. And I've already told you about a galaxy that only has a brightness of about 10 million times that of the sun. So billions of stars is obviously way too big for many of the galaxies that we're talking about. Finally, and this is just really semantics, but almost certainly galaxies have lots of solar systems, but we've never found a solar system outside of the Milky Way. So it is just speculation. I mean, almost certainly they will have solar systems. It would be weird if the Milky Way was the only galaxy with planets, but we don't know that for sure yet because we haven't found any extragalactic solar systems, but that would be super cool if we're ever able to do it. Okay, so this definition is clearly wrong, but I think it very well sums up the kind of thing we think about when we think about what a galaxy looks like. And normally, I think when, and you also shouldn't always trust NASA. So I think what we would all picture when you think about galaxies, things that look much more like this. So this is a huge mosaic of different images taken with the Hubble Space Telescope of sort of famous nearby galaxies. And it looks exactly what we think you kind of expect. The beautiful spiral arms, central bars, bright bulges right in the middle. Some of them are interacting, like the antenna down here. This is two galaxies merging together. Some of them look a bit weird and wonderful, but they're all full of stars and the gas and dust as well. You can even see dust lanes in for example, this galaxy here. Hopefully you can all see my mouse. Yes. And this is, I think, kind of what the definition that NASA is talking about. It's basically a definition of massive galaxies and what they look like. But, if you go down and down in luminosity, you start to see things that look rather less inspiring than these fantastic galaxy images. And this is, again, Fornax, which, again, as I said, is quite bright in my definition of a galaxy. But you don't see all that gas, that dust. You don't see any real structure either. You can see a couple of small star clusters in Fornax. There's one here, for example, and one here. But otherwise, it looks like sort of a ball of stars. And that's because it's what we call a dwarf spheroidal galaxy. So the key is in the name, dwarf, small, spheroidal, round. And we have a whole bunch of these in and around the Milky Way and in around the local group. And probably by number, these are the most common galaxies in the universe. But they only make up a tiny fraction, of course, of the stars in the universe. Most of the stars in the universe live in galaxies that look a lot like our Milky Way and these big things in the background. So you might wonder, why do we want to think about these very small galaxies? Like, it's cool to know that they're there. Sure, there's loads of them, but if hardly any of the stars live in them today, what do they really contribute to the universe? Very little in terms of their mass. But it turns out they can be very useful when we're trying to learn about other things. And there are a ton of them nearby, which means we can study a lot of them in great detail. Now, given that I've said that galaxies can be as small as Fornax with 10 million times the light of the sun pumping out of them, how low can you go in terms of like the number of stars in a system and call it a galaxy? Because historically, we probably wouldn't have thought we could find galaxies as faint as we do today, but we're finding more and more of them with new surveys. And we run into this problem where the sizes and brightnesses of these galaxies that we're finding are somewhat similar to the sizes and brightnesses of much more normal star clusters that we see, again, everywhere in the universe. So almost all stars are born in clusters, and clusters like this on the right-hand side here, this is actually a globular cluster. So this is a very old cluster of stars that sort of lives out in the outskirts of the Milky Way's dark matter halo, so sort of outside of the disk. And we think these things formed very early in the universe, and they're just collections of stars. And we've always said that historically, those are very different. While they are collections of stars, like galaxies are collections of stars, they're two very different types of collections of stars. So we have two different categories. And when you get small enough and faint enough, normally we say you're a star cluster. But at what point do you transition from star cluster to dwarf galaxy? And how do we define that division? And historically, that was very, very easy to do because they had this very nice clean boundary between them. So now I'm just showing a plot, and actually, I don't know if we can make this bigger because it's just cutting out the bottom axis. How do I do this? View, probably. Aha, there we go. So this is a very simple plot that just shows the size of things versus their total brightness. And on the left-hand side in the solid black points, those are all star clusters, and they are small, and they have a range of luminosities going from relatively faint to quite bright. And on the right-hand side, we have what I would call the classical dwarf galaxies of the local group. So you have some of them, the gray points are ones from around the Milky Way, the black triangles are the ones around Andromeda. And those are dwarf galaxies. And you can see that they kind of inhabit very separate planes in this diagram. So before the year 2000-ish, you had this very neat separation where you could, if you're on one side of this graph, you're a star cluster, and if you're on the other side, you're a galaxy. And you don't need to know anything other than how big it is and how bright it is to make that distinction between the two. You have this nice zone of avoidance between the two populations. But around the year 2000, a survey called the Sloan Digital Sky Survey began, which sort of upended all this. And Sloan was super cool because it was the sort of the first very wide field survey of the sky using CCD images. And it allowed us to go far deeper in terms of the image quality than we were able to do in the past, and very quickly scan for new objects that we were finding and sort of automatically classify things as stars and galaxies and so on. And when it switched on, not that long afterwards, it found a bunch of stuff that sat in this nice zone of avoidance between star clusters and dwarf galaxies. So you could see it as either being an extent downwards and upwards, downwards in luminosity and upwards in size from globular clusters, or downwards and downwards in size and brightness in terms of galaxies. And so when they were first identified in images alone, it was unclear whether they were galaxies or star clusters. And so we have now got the zone of confusion, where we have to have some way of defining whether these things are galaxies or star clusters. Now, I've already color-coded some of them here. So the big gray points are confirmed galaxies, and the open points are ones that we don't know what they are yet. But you can see there are places where you have galaxies and star clusters sitting side by side. So just with these two pieces of information, we can no longer determine which is which. And that means we have to find a new way of very simply classifying what's a star cluster and what's a galaxy. And it's very challenging. So we're going to play a fun game now. And this is what I play with my third-year cosmology students as well. They love it, I'm pretty sure. So we're going to play galaxy or star cluster, where I'm going to show a series of images and have you vote whether you think they're a galaxy or a star cluster. And you can become astronomers like me who are confused by everything all the time. Right. So we'll start nice and easy. Raise your hand if you think this is a galaxy. Good. Everyone recognizes Andromeda. That's my favorite galaxy. But, I mean, it's mostly in the talk just because I love Andromeda, and you always have to have an Andromeda image in the talk. So we can all agree this is very clearly a galaxy. So we've all got a point. All right, next one. Is this object a star cluster or a galaxy? Now, raise your hand if you think it's a galaxy. Couple of brave hands going up. Raise your hand if you think it's a star cluster. I knew the amateur astronomers would be good at this. Right, so this is indeed a star cluster. So what's kind of makes it sort of more obvious, it's hard to see because of the scale size of the image itself, but it's quite a dense collection of stars. And typically globular clusters, star clusters, they're very dense in their centers. All the stars kind of sink to the middle. But as you go into the zone of confusion, this clear distinction becomes less obvious. So now, what do you think this is, a star cluster or a galaxy? Raise your hand if you think it's a star cluster. A few hands going up. We've got, I think, most of the room. Okay, raise your hand if you think it's a galaxy. About the other half of the room is now going up. All right, so I think we're split maybe 2/3, 1/3, maybe 50-50. This one is a galaxy. This is the Leo T galaxy. So it's a very unusual dwarf galaxy right on the edge of the Milky Way's halo that is very faint, that seems like it formed stars recently, which we don't fully understand because it probably shouldn't have. Now, is this one a star cluster or a galaxy? Raise your hand if you think it's a galaxy. A few hands going up. Star cluster? Many more hands going up. Now, this one's particularly interesting because when it was first discovered, two teams found it separately. One called it a star cluster and one called it a galaxy. And in the end, with more and more data, we eventually landed on the fact that it is in fact a star cluster. So this is Levin's one. At some point, it was called Crater 2, I think. Crater 2, Crater 1, Crater 1. And yeah, the two competing groups interpreted the stellar populations in the object slightly differently. So one thought it showed more extended star formation, which would probably make it a galaxy. The other thought it didn't show that, so it would be a star cluster. And it took, I think, 2 separate campaigns of spectroscopy and really deep imaging from the Hubble Space Telescope to sort this out. So it's a very hard game to play. But that one is a star cluster. Okay, now finally, this is my favorite one. One of these images is a galaxy, and one of them is an empty patch of sky. So you have to vote on which one you think the galaxy is in. So if you think the galaxy is in the image on the left, please raise your hand. A few going up there. And what do you think? Who thinks it's on the right? A few more going up there. Well, I think this has gone better than for my cosmology class, actually. So this is indeed the one on the right is the galaxy. So this is SEGUE 1, which is the faintest galaxy. And I put an asterisk there because it's probably the faintest confirmed galaxy, but we have a bunch of things that could be galaxies that are fainter than this. Now you're scrutinizing it, you can probably convince yourself that you see maybe slightly more bright stars there than an average patch of sky, but I can guarantee that almost every star you might think is part of this galaxy isn't. These ones highlighted in green are the brightest stars in SEGUE 1, and this is the galaxy. So if you add up all the light in the stars in SEGUE 1, it makes up maybe 1,000 times that the luminosity of the sun. So only 1,000 times, so in fact fainter than one single giant star. This whole galaxy puts out less light than Betelgeuse. So that's a bit mad. Now, SEGUE 1 and objects like this are really sort of challenging our ideas about how galaxies form, how faint can you form a galaxy, but interestingly, also showing us a lot about what the nature of dark matter could be in the universe. And that's something I want to talk quite a bit about at some point. I forget when the slide is. So this is SEGUE 1. This is the faintest galaxy we know of, but there are things we have found that could be galaxies that are even fainter than this. So when we return to the question of what is a galaxy, a few things have now become clear. The number of stars is a little bit irrelevant. If you can have a galaxy that's fainter than one individual star, then clearly you don't need to have some kind of number. And technically, we'd probably never be able to find it if it existed. You could probably have a galaxy that was composed of a single star. That would be okay. No, it wouldn't actually. It'd be very offensive, but it would be allowed. The size of the object is also not important. As you see, they overlap beautifully in size and luminosity with star clusters. So you can go arbitrarily small, although there is a limit to this that we think is set by dark matter, and we'll come back to that as well. So what really matters for whether or not something is a star cluster or a galaxy is how the stars in the object are held together. What keeps them bound to one another and stops them from just dissolving into space and becoming part of the night sky. And so for galaxies, well, for star clusters, we think it is the stars themselves. So star clusters are just, as they say on the tin, clusters of stars. They only contain stars. And the thing that holds the stars together is the other stars in the system. So there's enough self-gravity amongst the stars in the system. They're in a small enough space that they can feel the gravity from one another, and that keeps them bound together. And in objects like this, you can see how that would be true. They're very dense. So that's really what's holding them together. Now, as you go up in size, but maintain the same luminosity, obviously you're pulling everything further away from each other, and gravity falls off like 1/r². So then the further apart the stars are, the more likely they are to just dissolve and go into free space. So if you want to have something that's quite diffuse and with very few stars, you probably need something else to hold those stars together. And in galaxies, the thing we think that holds them together is dark matter. So who knows what dark matter is? I was really hoping someone would know. Oh, none of us know. Okay, so I also don't know what dark matter is, but we as astronomers have known about the concept or the idea of dark matter for many decades now. It was first kind of posited way back in the, well, the term was coined way back in the 60s, 50s, 40s, a long time ago, by Fritz Zwicky, when he was measuring how fast galaxies were moving around in the coma cluster. So a big cluster of galaxies. He was measuring how fast the galaxies were orbiting around each other. And in an ideal world, you can actually measure a mass from how fast they're all moving around each other. So you can see, based on the speeds, how much mass there must be in the cluster. And you can also get an idea of what the mass in the cluster is from just seeing how bright all the galaxies are, adding up all the light, turning that into a mass. And you find that those two numbers don't agree with each other at all. So the two different ways of weighing a cluster give very different answers. With the dynamical mass coming from, driven by the gravitational interaction in the cluster, was far higher than the mass suggested by the galaxy's light. And so he said there must be some dark material around that was causing this effect, this faster rotation or speed of these galaxies. And since we see this a lot now, and basically every single galaxy that we can measure the motions of stars in, if you measure a mass from those motions of stars using the laws of gravity, you find that the mass enclosed is far higher than the number of stars would suggest. So we make up that there's this idea that there's this dark matter that doesn't interact with light at all, but is far more abundant than ordinary matter and is essentially holding galaxies together. So while we're not entirely sure what it is, we have some very good theories, we think it's extremely important for holding galaxies together and actually forming them in the first place. So we're going to say this is my dark matter halo, this ellipsoid here. And these tend to form very early in the universe. So right at the beginning of time, you're forming, hydrogen, helium, and some other light elements, and you're also forming a lot of dark matter. And the amount of dark matter outweighs the ordinary matter by roughly a factor of 5 to 1. Now, as the gas is being all hot and moving around and interacting with photons, the dark matter is just kind of evolving by itself and making sort of large clumps of dark matter. And because that's where most of the mass of the universe is, once the gas starts to cool down a bit, it feels the gravity of the dark matter and essentially follows wherever the dark matter is. So the dark matter can then sort of take the gas and concentrate it in a dark matter halo. And once it's there, it can then begin to cool down, spin into a disk, and eventually form a whole bunch of stars. And then these stars live in a much more massive structure that we call a dark matter halo. And that dark matter halo can stop the stars from flying off into space, keeps them bound to each other, well, keeps them bound to the galaxy, but it's the dark matter that's kind of holding them together. Now, in the very center of galaxies where you have loads of stars, then they also stay together because you have lots of stars. So like in the Milky Way, where you've got a big disk and a bulge, there is a lot of self-gravity from the stars themselves as well. But in these very faint systems, it's the dark matter that's stopping them all from flying apart and populating the night sky. So this sounds slightly wild, but this dark matter theory actually does really well at explaining a whole bunch of our observations in the universe, especially on the really big scales. So if you assume that dark matter is real and it outnumbers ordinary matter about that factor of 5 to 1, and it's made of a relatively massive particle, which is our starting assumption, you can run a simple simulation. I say simple, these are actually very difficult simulations to run, where you just put that initial starting condition, some amount of dark matter, some amount of ordinary matter, and then you hit go and you see beautiful galaxies forming in exactly the way that we see galaxies forming in the universe. So this is now a simulation of a Milky Way forming. All this red stuff is the dark matter, and the blue is the gas that's going to turn into stars. Now, the dark matter tends to form in this sort of filamentary way into what we call the cosmic web, with big knots of dark matter wherever the filaments overlap. And it's those big knots that end up being the big dark matter halos. Now, because that's the most dominant stuff in the universe, the gas then just falls into all the dark matter structures and then just follows the cosmic web towards whatever is the most massive thing nearby, which is usually something like the Milky Way here in this simulation, which is pulling in all the other smaller clumps of dark matter and gas to itself to grow into a more and more massive galaxy over time. So essentially what you have is a bunch of small galaxies early on in this cosmic web that get pulled together to form more and more massive galaxies over time. And then you end up with a universe full of things like the Milky Way. But you also end up with a lot of leftover small galaxies, which are these dwarf galaxies, that have not yet got fully sucked into the center of the Milky Way and can still exist as these tiny little galaxies in space. And by number, again, they significantly outnumber other types of galaxies. So this is how we think, this is what we think is going on. And what it means is dark matter is like the seed for galaxy formation and also kind of the scaffolding that keeps galaxies together. And if you run big simulations like this, you find that it really nicely reproduces the distribution and properties of galaxies on really large scales. So while we still don't know what dark matter is, having something like it seems to form a universe that looks a lot like our own. Okay, so how do we know if there's dark matter in a system like a star cluster or a dwarf galaxy? It's very similar to what Fritz Zwicky did. We just measure how fast the stars are moving and try and work out then how much mass there must be in the system and how that compares to the amount of light in the system. So first of all, if you have a galaxy or a star cluster like these two here, you can take a beautiful image, work out the brightness of all the stars, sum that all up together, assume some sensible relationship between the mass of a star and its brightness, and then you have a mass in stars for that object. Then you take your spectrograph and you measure velocities for as many stars as possible in your system. And then you use simple gravitational laws in order to work out, given the speed, what the mass enclosed in the system must be. And then you can compare those two different masses to one another and you see if they agree. If they agree to within a factor of a couple, probably you're looking at a star cluster. However, with the dwarf galaxies, what's interesting is that they tend to disagree on a much larger scale than galaxies like the Milky Way. So in galaxies like the Milky Way, maybe the ratio is 5 to 1. In these systems, it's much more like 10 to 1, so 10 times as much dark matter, even in their very centers, as ordinary matter, and can be as high as thousands times more. So for SEGUE 1, its mass to light ratio is something like 3,000. So 3,000 times more dark matter in the center of the galaxy than stars. And that's basically how we now distinguish between these two things. You have to know whether or not they're dominated by dark matter. And that can be very hard to measure the fewer stars you have in a system. So that's why I said you can have a galaxy with only one star in it. But if you can only measure the velocity of one star, you don't really know what that's relative to. So you can't say if it's definitely dominated by dark matter. With two stars, you might be able to do it, but you might just be unlucky that they are moving in a way that you can't either measure the spread or you measure too big of a spread. So the number of stars sort of limits how well you can measure the mass of the system. And that's why a number of those objects on that plot I showed you before of size versus brightness are still as yet unclassified, because they have so few bright stars that measuring the amount of dark matter or lack of dark matter in them becomes extremely challenging with current equipment. But we thus define galaxies as things that are held together by dark matter. And if you don't believe in dark matter, which is fine, professional astronomers sometimes don't either, they cannot be explained by just ordinary Newtonian gravitational laws. So you have to appeal to maybe some kind of modification of gravitational laws instead. I prefer the dark matter theory because it's a bit more complete. MOND is really cool, so modifying gravity is cool, but it can't explain how galaxies form, whereas the dark matter model is a bit more complete in that sense. So to me, it makes a bit more sense, but it doesn't mean that it's right. Until we detect the particle, it's quite hard to say what's really true. All right, so we've established how we define galaxies now, even when they're as small as the ones I've been telling you about, but why should we even care about them? And this is also something that gets raised at conferences I go to. So this is my colleague, Professor Alan McConaughey. Together, we've discovered many dwarf galaxies over the years, especially ones around Andromeda. He's very much a leading expert in finding really tiny galaxies. And at the last meeting I went to with Alan, it was in Potsdam, and someone had just found an object that could be a galaxy that's even fainter than SEGUE 1. And Alan said, these galaxies are so faint, we should all be offended by them. And I am a little bit, because it makes it really hard to know what's going on with them. But, you know, just because they don't look particularly impressive doesn't mean we can't learn a lot about physics from studying them. And in fact, even just counting how many of them there are can be one of the most informative probes of dark matter that we have at the moment. We just have to know that they're really dwarf galaxies, and that's the tricky part. So we think they're important because they can tell us about the properties of dark matter. And that's because the properties of dark matter itself, the nature of the dark matter particle, has quite a big effect on how the smallest structures in the galaxies form, the smallest structures in the universe form, so the smallest galaxies. So for one, the mass of the dark matter particle at some point has a limit to how faint a galaxy, or how low a mass galaxy you can form. So there is some limiting galaxy mass that is set by the property of dark matter. And it's really kind of getting beyond almost what we can measure. But if we can measure really faint galaxies or really small galaxies, we can start to get the idea of what the dark matter particle is. The nature of dark matter also kind of affects when you can start star formation in the universe, because in certain models, the dark matter halos will form sooner, so you start forming galaxies and stars sooner, and in other models, it's slightly delayed. And that's particularly interesting right now, because I'm not sure if you've all been reading about results from JWST, but JWST seems to be finding lots of very massive galaxies a bit earlier than we were expecting to see them. So it seems like star formation in the universe may be much more efficient than our current models predict. Now, it could be that there's something we don't understand. My computer's doing something weird. My slide's still there for the moment. We'll figure this out. It could be that there's something weird we don't understand about star formation, because there's loads of physics that goes into star formation that we don't actually understand yet. And it could be, though, instead dark matter. Zoom seems to have crashed on my machine. We'll figure this out. Okay. So yeah, so it could be telling us if we are seeing all this very rapid galaxy assembly very early on, that could be pointing to a problem either with our understanding of star formation or with dark matter. So trying to figure that out is very important, and that will, any kind of insight to that will lead to more information about what dark matter could be made of. And it also dictates the number of faint galaxies we should see. So the number of SEGUE 1s that exist in the universe is dictated by the dark matter particle mass, because you're getting to the very hairy edge of what a galaxy could be, and therefore the nature of the dark matter particle is related to that faintest galaxy and how many of them you can see in the universe. So if we can just go out and find them all, we can start to say cool things about dark matter. And that's why we should care about them. Also, they tell us a lot of stuff about star formation too. and the chemistry of stars in the early universe, and reionization. But I don't have time to talk about everything, so we're going to focus on dark matter for now. But if you have questions about any of those things, I can probably talk about it for ages after the talk. All right, so just by counting galaxies, we can learn about dark matter. And this is sort of a bunch of stills from simulations that sort of show this somewhat qualitatively. So at the top left, all of these panels here are dark matter simulations of a Milky Way galaxy. So sort of the big yellow glow, that's the Milky Way. And then around it in each realization, you can see smaller purpley blobs. And those are small dark matter halos orbiting around the Milky Way-like massive galaxy. So they're bound to the galaxy, but they're their own little dark matter halos. Now, not all of these purple blobs will form galaxies, because some of them will be too small to cool gas and make stars, but they should exist out there in the halo. And if you change the nature of the particle, you will change the number of those purple blobs you can see. And it's most evident between the top left panel and the two bottom panels. So the top left is our current preferred model. This is the cold dark matter paradigm. And cold just means the particle is pretty massive, so much bigger than, say, the Higgs particle, way bigger than a proton. And because it's massive, it moves slowly. So we say, it's edgy room again, I'm sorry about it. Oh, I'm back already. Yeah, so if it's massive, we say it's non-relativistic, so it's moving very slowly. And what that means is it's much better at clumping and creating structures. So it can form far smaller dark matter halos if it's moving slower. The slower the particle moves, the smaller the dark matter halo you can make by dark matter particles sticking together, because they're just not moving very fast. As you make the particle lighter, they become more relativistic, so they move faster and it's harder for them to clump. So they will make fewer small structures. And so in the top left, you can see there's loads and loads and loads of purple blobs around that yellow glow. But in the bottom two, where we've made the particle warm, so a few orders of magnitude less massive, there are many fewer purple blobs. And so you dramatically reduce the amount of structure around the Milky Way. Now, it still has the most massive objects around it, and those are the kind of dwarf galaxies that we can easily find. So in that way, they're very consistent. Both of these models could be true around the Milky Way. But as you start to move down to SEGUE 1 type masses, and even a bit higher than that, a lot of those objects disappear from the warm dark matter model. So if you only have one SEGUE 1, it's probably fine. If you have hundreds of SEGUE 1s, you can rule out a warm dark matter particle. It's just not possible. And then the final one there on the top right, that's self-interacting dark matter, where you can have a similar mass to the cold dark matter particle. But normally we say dark matter only interacts gravitationally and through no other force. But you could imagine a scenario where dark matter can slightly interact with itself. So as the two particles get close to each other, they feel a bit of repulsion. And then you would maybe expect to, again, form slightly fewer of these purple blobs. So it's less obvious here, but in the self-interacting dark matter model, there are also fewer SEGUE 1 type galaxies. But it's not quite as dramatic as the warm dark matter case. So if we know how many SEGUE 1s we should have from a simulation in any dark matter model, and we know how many we have in the real universe, we can begin to rule out different types of particles. And because the particle physicists haven't done anything for dark matter yet, that should really help them design better experiments so they can be more successful. But then what we have to do is find all of the SEGUE 1s, and that's very hard. The only reason we found SEGUE 1 in the Sloan Digital Sky Survey is because it's relatively nearby. So most of its stars are extremely faint, which makes them hard to find if you put it, a factor of 10 further away, because they're just too faint to really stand out in your telescope images. Because obviously this is it's very clearly standing out here, very obvious. But it is challenging. So we were lucky to find this one, and we are now with slightly deeper surveys starting to find a few more things like it. But we would need to find many more and be sure that we are complete in our observations to really start to make a difference in our understanding of dark matter. So because it's offensively faint, it's very hard to find. Right, so in terms of how we tend to find them in surveys, you can look for these things visually, and I will talk about doing that in a moment. It's extremely painful and time consuming, but we also have some methods that for the galaxies we've been finding thus far do work, but they are starting to break down as we move further away, and we'll talk about that too. But the technique we use is called match filter, and the last time I tried to explain this, I did a horrible job of it. So if you have questions at the end and don't understand it, it's definitely on me, because I still haven't got any better at explaining it. But essentially, with match filter, you're looking for two types of association. One, you're just looking for you basically take many filters on your telescope and take images of the same patch of sky in all those different filters. So in Sloan Digital Sky Survey, for example, we use the UGRI Z bands, which is ultraviolet, green, red, infrared, and Z band. I'm never really sure what the Z stands for. And typically you'll image the sky and make a color magnitude diagram of at least, compare the brightnesses in at least 2 filters. We tend to use for dwarf galaxies some combination of G, R, and I. They're the most effective for kind of pulling out the features of a dwarf galaxy. But first you make your sky maps. You image in both filters, you decide what you think is a star in an image, and you decide what you think a galaxy is, and then you can make a density map of what the universe looks like in either stars or galaxies, and you can look for clumping. So for these galaxies like SEGUE-1, we want to look for clumps of stars. So you can make a little density map of all the stars in the field of view and all the galaxies. So on the left here, you can see I picked an area of sky where there's an overdensity of stars, and in the galaxy map, there isn't an overdensity. And so probably what you're seeing here is some association of star. Now, we don't know yet if this is just a chance alignment, that happens a lot, or a poorly defined, very distant background galaxy cluster, which also happens a lot, because the further away your galaxy cluster are, the more the galaxies start to look like stars. So if you really want to know if this is truly an association of stars, you then have to take the images that you've made in multiple colors and construct what we call a color magnitude diagram to look for a stellar population that likely is a dwarf galaxy or a star cluster. And in that case, what we assume about all these galaxies is because they're so faint, they tend to form all their stars very early on in the universe. They have a very similar age, and they have a very similar chemistry. They follow very similar stellar evolutionary lines in a color magnitude diagram. So this is an example of a color magnitude diagram. This is actually of a star cluster, and it's got extremely good data that we don't tend to have quite this good data for things like SEGUE-1. But what you're looking for when you make the color magnitude diagram, so on the x-axis, you have the color, so it's just one filter minus another filter, so the brightness in both. And if you're redder, you tend to be an older star. If you're bluer, you tend to be a younger star, because old stars tend to be red and sort of cooler, whereas the young stars tend to be very bright and massive and blue. So you get an idea of a little bit of the age there, and then you plot that color against the apparent brightness in one of your filters. So we often go with G minus I for the x-axis, and then I band magnitude on the y-axis for dwarf galaxies. And then you can see if they're all from a similar stellar population that grew up at a similar time with a similar chemistry, you'll see something that looks a lot like this, where you have a main sequence where all your sort of, sun-like stars are evolving happily, but burning their hydrogen, turning it into helium. And then as they run out of hydrogen, they turn off the main sequence and ascend the giant branch. So you'll get a lot of bright red giant branch stars. And then you'll also have this horizontal branch feature, which tends to be very prominent in old systems. And this is where you get helium burning stars, essentially. So this is the kind of pattern you're expecting to see. And then depending on how far away your object is, you might only see the red giant branch. So then you have to use only this population to convince yourself you've got some kind of real association of stars. If you're lucky, you get down to the horizontal branch, because that's a little bit more populated and it's a very distinctive feature. It can also be used to measure the distance to the object, which is extremely helpful. And if the object is very nearby and you have deep imaging, like what we had with SEGUE-1, you might get down to the main sequence. And that's the best scenario, because most of the stars are there. So that's much more obvious. If you only have a very low mass system like SEGUE-1, it doesn't have very many giant branch stars. And that makes sense because it's fainter than a single giant star. So you really need to get really deep down to find things like SEGUE-1. And that's why typically we've only found them very nearby. But this is how we then use this match filter technique. You can automate this to get your computer to just run through a whole bunch of catalogs of data, assume everything is, look for a clump of stars, assume a bunch of different distances, and see if you can tease out this color magnitude diagram shape. And that's how we found SEGUE-1. Well, I didn't find it, but how astronomers found SEGUE-1. But this tends to break down when you put SEGUE-1 further and further away. And that's why we've had to use other techniques now to sort of try and find faint galaxies to really convince ourselves that they're in the data or not in the data to see if we can put constraints on dark matter. And we want to do this to solve also the missing satellite problem. So the hunt is on to find these faint galaxies and to really understand if our number of galaxies matches our expectations. And for a long time, it hasn't. And this has been known since the late 90s as the missing satellite problem. And this is just if you take your observations of dwarf galaxies, which are the points here, you can make a cumulative number distribution of them. So to see how many you have as a function of mass, which is the x-axis here. And in the late 90s, we knew of about 10 dwarf galaxies total around the Milky Way. But if you ran a dark matter only simulation and looked at the cumulative distribution of dark matter halos of the same mass scale, the dashed lines of what we're expecting for something like the Milky Way. So there is a huge difference between the number of galaxies we were seeing in the late 90s and the number of dark matter halos we were expecting from the simulation. So it's, you know, an order of magnitude or more. Now, this is not exactly fair comparison, and it was known even at the time, because you're not comparing like with like. First of all, when you're looking at galaxies, you can only find things that have stars, because that's, you know, it's a prerequisite. We can't see dark matter as yet. Whereas in a simulation, you can find anything you want to because it's in your computer and it will tell you that that dark matter halo lives there. But it doesn't necessarily tell you that dark matter halo would have formed stars, because these are pure dark matter simulations, because we couldn't do all the gas physics that we can now do. And it also doesn't tell you how bright they should be and whether your telescope should be able to detect them. And so a big missing piece in the late 90s was that we knew we weren't finding the faintest galaxies because the technology we had wouldn't allow us to. So over time, this missing satellite problem has become far less serious, and it's been one of another piece in the puzzle of explaining that we think cold dark matter will work reasonably well, even for dwarf galaxies. So this is a more modern version of the plot. So now the simulation predictions of those two shaded bands in this plot. So again, we're just looking at the cumulative number of satellites as a function of halo mass now, so the total dark matter mass of the system. Now the blue line is for all the galaxies around the Milky Way that we know we're complete in our survey. So we've definitely found everything at that brightness. So the blue line extends to about this halo mass of 10 to the 9 solar masses, and it's in pretty reasonable agreement with the simulations. If we add in then the fainter galaxies for which we know we're incomplete, things like SEGUE 1, that gives you the green line, and you can see then we have even more satellites, and again, it agrees really well with our predictions, down to about this 10 to the 9 solar masses in dark matter halo mass. So right around this point, we would say the satellite problem is fixed, because we have enough satellites to satisfy cold dark matter models. But right where it's getting interesting is right where we're getting incomplete with our data. So if we could convince ourselves that that green line told us everything, that was everything that we had around the Milky Way, that would tell us that then we don't have enough and cold dark matter needs to be wrong. But we don't know that. We have to look for these dragons and try and find them. And the match filter technique is beginning to fail for anything that's a bit further away, because you don't have enough bright stars pop out in your images for your computer to be sure that it's detected them. But it turns out there is something that's better than the computer for finding these faint objects, and that is human eyes. It is much slower and more painful, but we've been doing this now for a while with an amateur astronomer named Giuseppe Donatillo from Italy, who has been scanning a bunch of surveys, including the DESI Legacy survey, which is an imaging survey that is not at all designed for finding dwarf galaxies, but does cover most of the sky. It was actually designed for a big cosmology survey, which is using a spectrograph to measure the velocities of many, many distant galaxies to constrain things like dark energy. But at the same time, you can scan all these images to try and find these very faint dwarf galaxies. Now, because it's not designed for finding faint dwarfs, the match filter approach is really, really bad. But Giuseppe's eyes are second to none. So we have found a few faint dwarfs from just visually scanning in regions where we suspect there probably are dwarf galaxies hiding, because they should be there, and then seeing if we believe they're there or not. So this is a really good example of how I think Giuseppe might be a wizard. So on the left image here, this is the DESI image of a dwarf galaxy called Pisces 7 that Giuseppe found. And the first time I was shown this image by him and his colleague David, I was like, sure, whatever you say, great, yeah. 4.4 meter telescope at it. And so on the right-hand side, you can now see the image from the 4 meter. And if you look right in the very center, there's a small puff of little stars. And that is the dwarf galaxy Pisces 7. And it's super cool because, one, it seems to be a satellite triangulum, which is famously missing small dwarf galaxies around it. That's why we looked in that area. So it seems like now it has one, which is very cool. And also, it's very faint, and we think it shouldn't be forming stars anymore. But from our first imaging, it looks like there may be some young stars there. And if it is, that goes against what we expect for galaxies this faint. So we could learn something really cool about star formation and reionization. But again, I don't have time for that. But we can talk about how cool Pisces 7 is later. We also found Pegasus 5, which is similarly very obvious to Giuseppe. So in this upside down smiley face, you might notice that in the DESI image, there's a slightly brighter in the center than it is in the outskirts. And then again, when we pointed this time an 8 meter telescope at it, we again saw a small cloud of stars right in the center. And when you measure the color magnitude diagram and the structural properties of this object, it does turn out to be another dwarf galaxy. This one is orbiting around Andromeda. And it's cool because it's kind of the opposite to Pisces 7 in that it seemed to form all of its stars extremely early in the universe. So it had a short burst of star formation and then did nothing for about 13.5 billion years. So it seems to be a fossil of one of the very first galaxies. And if we can measure the chemistries of these stars, we can start to put real constraints on what star formation was like right at the beginning of time. And because it's only a mere 785 kiloparsecs away, we can actually get very high resolution data for these stars, which is something you cannot do for galaxies like JWST is finding, because they are right at the beginning of the universe now. So they're super cool and very complementary. But here we might be able to get into some of the real details of chemistries of individual stars in a way that JWST cannot currently do, which is neat. We also have a bunch more candidates. These have not yet been, well, we have some follow-up data for them. As again, these are very convincing Giuseppe images again. And in the middle here, candidate 2 looks an awful lot like in our deep 8-meter imaging, a SEGUE 1 candidate, but much further away, which would be really neat. But because the main sequence of stars there is right at the point, so it's very, very faint, and it's right at the point where it's really easy to confuse stars and galaxies, we can't be 100% sure that we found it. But if we have, that's actually big news, because there is one theory that things like SEGUE 1 are only nearby the Milky Way because they're sort of the remnants of galaxies that have almost been destroyed. But if we find them everywhere, it means they're a real population, and that will really help us better understand dark matter again. So what we need to understand if these things are real is to go even deeper with, like, say, Hubble. And the Hubble panel met last week, so hopefully soon they'll be telling me that I definitely have time to spend peering at the faintest galaxies in the universe. So if I come back next year, I'll have to let you know if I was successful or not. Hopefully I will have been. Okay, so what's coming next? So HST data would be great. Scanning these plates with your eyeballs is fun, but very time consuming. But we are going to get a much deeper survey that should better clarify for us some of these very faint systems without us having to squint at them the way we are with the DESI Legacy Survey. And in particular, the Vera Rubin Observatory should help with that. So this is an 8-meter telescope that's being constructed in Chile. And it's going to do a whole survey of the southern sky over 10 years. And because it's an 8-meter telescope, it's going to be way better. It's going to be able to go way deeper than the Sloan Digital Sky Survey, than the DESI Survey, than the Dark Energy Survey, or any of the other surveys we're using to look for these dwarf galaxies. And so basically, this telescope should be able to find all the segues everywhere. And if it doesn't, and either way is interesting. So if it does, we'll know that cold dark matter is right, and we have the right number of small galaxies in the universe. But if they're not there, this telescope should find them. So if they're not there, we know that our model for dark matter will be wrong. So in the next decade, this should be a problem that can be solved just with this telescope alone. There's actually a bunch of other cool telescopes that will help in the meantime as well, but we are within, I think, the point of knowing, in my career, hopefully, whether or not cold dark matter is the correct model for the universe. Or, well, whether or not it's the incorrect model probably is a better way of putting that. Until we find the particle, we're never going to be really sure, but hopefully one day we'll get to that too. Okay, so that brings me to the end of the talk. So the faintest galaxies in the universe don't always look impressive, but they're really incredibly useful. They can teach us a lot about dark matter. And I think in the next decade, we're going to find, or not find, a ton of these galaxies. And that's going to be extremely exciting for our understanding of the universe. Thank you very much for having me.
That was great talk. Normally at a moment, I'd ask the question and I'd run around with a microphone. But since you've only got one, we'll have to ask the question and then maybe I
can repeat them. Yes, yeah, okay. Oh, dark matter, the nearest, so what is the nearest dark matter halo to it? That's a good question. So SEGUE 1 is amongst the nearest, probably. For example, the Sagittarius dwarf galaxy that's being pulled apart and is very close to the bulge right now, that still has some of its dark matter left, and it's smearing it all over the sky as well. So there's sort of, that one's being destructed around us, I guess you could say. But yeah, I mean, technically you could have one pass through the solar system. And you may not notice depending on how big it is. If it's too big, you'd definitely notice, but because they're quite puffy, they could be everywhere. There should be dark matter everywhere. And small halos, if cold dark matter is right, you can have dark matter halos that are as small as the Earth. So one could ping through the outskirts of a solar system, we wouldn't even know. Well, we only know about the ones that are hosting the luminous galaxies for sure. Everything else we haven't been able to detect, but there definitely are a whole bunch of them in the outskirts of the galaxy. But in the disk of the galaxy, nothing, we can't say concretely that there's anything in the disk of the galaxy. Well, so with the dark matter halos host the galaxies. So something like SEGUE 1 lives in the dark matter halo. So we infer that it's there because of the way the stars are moving within SEGUE 1 or within Fornax. So we know they're living in their own dark matter halo. But they're all, of course, outside of the disk of the galaxy, these ones. So they are within our massive dark matter halo, which extends well beyond the disk of the Milky Way. So they're part of the Milky Way system, but they're much, much smaller than the Milky Way's dark matter halo.
You talked about distinguishing between an open cluster and a small galaxy by counting calculating the total mass of the star.
Mm-hmm.
Supposing that had mass, a huge number of brown dwarfs that you could not see, but the mass that they have be attributed to dark matter.
So this is definitely something that was thought about quite a lot in the early stages of trying to work out what dark matter was. And so, yeah, in principle, right, you could have a whole bunch of, and not just brown dwarfs, you have black holes. And if there's nothing close enough to a black hole, you don't know it's there, right? So, but we think that that's fairly confidently ruled out in terms of using microlensing, basically. So you have these beautiful surveys of microlensing that have been used for a long time, which is where you stare at the stars in the sky and you wait for little things to go past them and make them wobble a bit. So you have a little microlensing event from something passing in front of a star. So if there were enough brown dwarfs or black holes rumbling around the Milky Way, we should see many more microlensing events. Now, there is still, we think, potentially enough small black holes that you could make up some chunk of dark matter with them, but not enough to explain the huge differences in mass that we see. So they can definitely be contributing some amount. And I think the latest estimates were maybe as high as 10-ish% of the total dark matter could come from very small black holes. So we call them primordial black holes. But otherwise, lensing puts a strong constraint on sort of the upper limit there. Because if there was tons of them and they were everywhere, is what we would need. And then you'd see microlensing happening all over the show. No problem. So Euclid will help as well. So we've been talking more and more about using Euclid for this. So one problem with Euclid is that it's trying to avoid looking near very massive galaxies nearby, because it's obviously trying to look at very distant galaxies to measure how the universe is on large scales. So in terms of targeting some of the galaxies that we think would be useful for finding some of these faint dwarfs, it's sort of avoiding them on purpose. But in the Milky Way, of course, along the line of sight, we may still find many of them around our own Milky Way with Euclid. And the imaging is so good that you don't run into the same problem that we have with ground-based imaging. Well, you run into it later, but one of the big problems you have in figuring out if something's really a galaxy or not from the color magnitude diagram is whether you're really seeing stars or you're seeing distant background galaxies, because at some point they look the same. And when you go through the atmosphere, it's at sort of the limit of the seeing of the atmosphere. But because Euclid is in space, it's much easier at faint magnitudes to distinguish between a star and a background galaxy. So it should be able to hopefully find a bunch of them nearby by accident. So we are looking into how we can use Euclid to do that, yeah. No problem.
So a lot of it is sort of stars and dark matter. But what would sort of happen if you threw a bit of nebulosity into it compared to a normal galaxy that's got nebulae?
So if you put nebulae into a dwarf galaxy, to a regular galaxy. So, I mean, at some point they probably would have had these low mass galaxies when they were very first forming stars. They would have had a lot more gas, and you could have had nebulae and things like that. The issue as you go to these very low masses is it's very easy for the gas to get heated up out of the system. So you lose a lot of that nebulosity that you might have had at early times. Either from, let's say, if you're a small galaxy falling into a big galaxy like the Milky Way is surrounded by hot gas, and that tends to peel all the cold gas and nebulosity out of a low mass galaxy. So then you lose it. But if you're living far enough away, we may start to see very faint galaxies that do retain some of that nebulosity. But it's very hard to detect it because it will be at a much lower level than what we see in massive galaxies. So it may be there in some of these isolated low mass galaxies, and that's something we would like to see, actually. There are a couple of faint dwarf galaxies that show a little bit of, mostly we can just detect H1 gas, so neutral hydrogen. We can find some hydrogen, or ionized hydrogen. So there are a couple, and so Leo T, which is one of the ones I showed in the Galaxy or Not a Galaxy, that's sort of the limit of the faintest galaxy that we've seen that still has some reasonable amount of hydrogen gas in it. So you don't really see it in nebula form, but you do see a slight clumping where recent star formation may have happened. So it is possible that some of the very faint ones still retain a bit of that gas, but they probably had to live a very isolated life to avoid having it pulled out of them. Yeah, no problem.
Didn't mention it. So is the motion of stars in star clusters and galaxies basically the same?
For the dwarf galaxies and the clusters, the motion is very similar. So because both of them are have very little rotation, so they tend to be much more sort of dispersion supported, so random motions in both. You can see a little bit of rotation in either system, but it's much lower level than the kind of random motions of the systems themselves. And that's probably just because they're so low mass that you just don't get sort of long-lived disky structures in them or rotating structures. It's easily washed out by one rogue black hole or something.
You had to already
mentioned at the start that gravity drops up as 1 over r squared. In terms of how do you decide whether dark matter acts in the same way as gravity instead of normal matter? And how do you decide it's not more like a treat ball that slows down the effect of normal gravity matter?
Yeah, so that's a good question. So how do we know that dark matter is behaving in a sort of normal gravitational way? I think in a way that's been a choice for us, right? So what we see is something that's very much mimicking what we expect to see from a huge amount of matter being somewhere. And if we assume that stuff is just like matter, but it doesn't interact thermally or with radiation, so it only interacts via gravity, it's kind of the simplest assumption you can start with. And then you find that if you just run that in a simulation, it produces large scale structure just as we see it. And it also agrees very well with the data we see from the cosmic microwave background in terms of there's a ratio there that you can measure for dark to ordinary matter. So it does a really good job, that assumption of just being ordinary, well, like ordinary matter and how it behaves gravitationally. But of course, there are competing theories, and the main one is sort of modifying gravity. So the assumption is that, you have Newtonian gravity and sort of general relativity up until a point, but on very, very large scales, like the scales of gravity, gravity might behave not as 1 over r squared anymore, but in some other way. And you can modify gravity at that point, and then you tend to reproduce some of the observations we see for like the rotation curves of galaxies, so how fast their stars are moving. And it does work very well for certain systems, particularly spiral galaxies and even some of these dwarf galaxies. But then it tends to fail in other ways. And it doesn't have a sort of cosmological framework as yet that could then explain. So with dark matter, you can go on the universe with it and it makes the universe. Well, it acts as the structure formation sort of mechanism. Whereas in modified gravity, you still need something that does that. And it's not clear what that would be that could still reproduce all our observations. So it's sort of an incomplete theory. So it could still be that gravity does modify on large scales, but you still would need something else then to explain sort of the wider evolution. So at that point, it's sort of an incomplete theory. But it does mean there are other options out there. It's just that the dark matter, the matter that is dark but acts just otherwise like ordinary matter, seems to do such a good job that we kind of stick with that.
Low surface brightness galaxies that you go after, what is the brightest of them in terms of magnitude? I was just wondering whether any of our instruments might be good enough to detect either image or vision. I suspect the answer is no.
I mean, probably yes. I'm sure that. Well, so I have looked at probably at the brighter edge of it. So. Yeah, so probably, I mean, at the scale of Fornax, for example, that's something that's easily detectable by anybody. As you move down to like SEGUE 1, yeah, then it gets much harder. So in terms of what the limit might be, I'm trying to think, my collaborator at UCLA has his own telescope as well that he set up, and I think it's 70 centimeters. And he has done some very nice integrated light imaging of some very faint systems, not quite as faint as this, but maybe to the level of like an absolute magnitude of 7 or something in terms of the total integrated light in the system. Yeah.
What's being done in the laboratory? I'm thinking by laboratory, a big public somewhere to try and discover what dark matter is.
So in terms of what the particle physicists are up to, at CERN, they do have some experiments that could potentially find a dark matter particle. We think it's unlikely. I think the particles that they are able to detect are not necessarily favored ones for what we think dark matter is. But there is a chance that they can test some models, some predictions for dark matter models. Some of the other particle experiments have really been tuned to try and find what we call WIMPs, which are weakly interacting massive particles. And they're a big favorite in cold dark matter because they don't only do all the cold dark matter stuff we need. They also solve another problem in the early universe. And I can't remember which way around this goes. So there's 2 particles that bring you an extra bonus. One of them is the WIMP and one is the axion. And one of them solves the charge parity issue that we have. And the other one solves like the matter to antimatter ratio. So the WIMP is a favorite one because it also solves another problem, and we could potentially detect it. And so what they use to do that is usually big tanks of heavy stuff underground that you wait to see something hit a particle and produce a little bit of light, and then you can say something's interacted with the tank. So a WIMP could potentially do that. So they use big tanks of xenon, liquid xenon underground, shielded from a lot of neutrinos and everything else that might hit them, and then they wait for little flashes of light, and they see if that's consistent with it being hit by a WIMP or not. And so far they haven't found anything. So they're making bigger and bigger tanks, but with time you're sort of ruling out more and more WIMP models. And I think there's a large feeling in the community now that even though the WIMP has been our favorite particle for a long time, we might have to let go of the WIMP. So that's one of the big favorite experiments that's been done in the past. And then there are some other ones looking at axions, but I'm not as up to date on what they're actually doing for axions at the moment. Yes, it is, and it's happening right now on Zooniverse, I think. So the one I'm aware of is also using this sort of it's doing match filter by eye. So you'll get like kind of like the maps I showed you, where you see like a little density of stuff, and then a color magnitude diagram, and you get training on whether or not you think that's more likely to be a dwarf galaxy or not. And that's part of a survey that I'm in right now called DELVE, which is I can't remember what the acronym stands for now, but it uses the Dark Energy Telescope in Chile to do a big mapping of sort of the local universe. And so now anything that's kind of, what they're doing is, because we know match filter breaks down at a certain point, it's taking a lot of stuff that the match filter algorithm is not sure about and putting it out for the public to have a look at, because we are better at distinguishing between the things that the algorithm's not sure of. So yes, you can definitely get involved with the Zooniverse. And I think it's called Delve. It's related to Delve somehow. Yeah.
If you have a slightly heavier dark matter particle, you'd also expect the cosmic background power spectrum to change. Is that detectable with the sort of matters you're talking about?
So I think that both warm dark matter and cold dark matter can reproduce the power spectrum. There's enough wiggle room there that I think you're okay. So it's more the ratio of mass between baryonic and ordinary. So as long as there's enough warm dark matter, it should be fine for the cosmic microwave background. I suspect at some point in the noise there is something that may be able to distinguish, but not from our current observations. So yeah, so there is a limit based on the CMB as to how light you can go. I don't know there's a limit. There must be an upper limit somewhere, but I'm not sure about the upper limit. Yeah.
Any more questions? Well, perhaps have one more. So,
the mass equivalent of dark energy current theory is completely overlaps everything else in the universe. Does it have any gravitational effect on the things that we're talking about?
So we think it doesn't. So dark energy, we think, has no real gravitational impact, right? Well, so we don't think it acts via gravity. It's sort of acting to accelerate the expansion of space-time. So in the future, dark energy will be a real problem because at the moment, it's too weak of a force to pull apart things that are gravitationally bound together. So it can move, it can stretch empty space, but it cannot stretch apart bound gravitational anything. So star clusters, galaxies, they're all, the gravity, even if it's weak, is overwhelming dark energy in anything that has a bit of stuff to it. In the far future, it's expected that dark energy will get better, will get faster and faster, it will pull things apart more and more, and you'll get to the point where it'll rip apart the whole universe. That's one model. That's the current favored model of dark energy. I think that's all very uncertain because we know even less about dark energy than we do dark matter. But if we follow the model to its natural conclusion, it eventually pulls apart the whole universe. So at some point, it will get strong enough to overwhelm even the forces that kind of hold, you know, atoms together. So it can pull apart the nucleus. But that is like way beyond timescales that any of us need to be concerned about.
Michelle, it's been a fascinating talk. Thank you. As you can tell, everybody's enjoyed the question. Thank you very much.